Welcome to Math on Ice, December 2013 Integral Equations. There are two questions from this, one question from part B and one question from part C. The first question from part B, the integral equation phi of x is equal to f of x plus integral 0 to 1 k of x comma y phi of y dy, where the kernel is given, we need to find the solution. Now, we will just write in our convenient form, y of x is equal to f of x plus integral 0 to 1 k of x comma t into y of t dt. This is our convenient form. Here f of x is unknown and the kernel is given to be k of x comma t is equal to xt squared. We solve by the resolvent kernel method. We will just evaluate the resolvent kernel r of x comma t comma lambda, which is equal to, here lambda is equal to 1, so we can have 1. So that is equal to summation n is equal to 0 to infinity lambda to the power n. So here we get 1 plus 1 to the power n, and then kn plus 1 of x comma t, where kn plus 1 of x comma t is equal to integral 0 to 1 k of x comma z into kn of z comma t into dz. The final solution is y of x is equal to integral f of x plus lambda over lambda is 1 here, so integral 0 to 1 resolvent kernel into f of t into dt will give you the solution. Now we will find kernels k2 of x comma t. So k of x comma t, this would be equal to k1 of x comma t. So k2 of x comma t is equal to integral 0 to 1 k of x comma z into k1 of z comma t into dz. So that is equal to integral 0 to 1 x into z squared into z into t squared into dz. That is equal to xt squared can be taken outside. This will be z cube 0 to 1 z cube into dz. That is equal to xt squared z power 4 divided by 4. Apply the limits. We get it as k2 of x comma t is equal to xt squared by 4. Similarly, k3 of x comma t would be integral 0 to 1 k of x comma z k2 of z comma t into dz, which will be integral 0 to 1. What is the k of x comma t? X comma t is k of x comma t is x t squared. So here we get x into z squared, and this would give you z into t squared by 4 into dz, which is equal to x t squared by 4 can be taken outside. Integral 0 to 1 z cube dz. Can we get it as x t squared by 4 z power 4 by 4. Apply the lower and upper limit. We get xt squared by 4 into 1 by 4. So that is xt squared by 4 square. So similarly proceeding, we get k4 of x comma t is equal to xt squared divided by 4 cube, and so on. Kn of x comma t is equal to xt squared divided by 4 to the power n minus 1, because for 4 we get 4 cube, and for k3 we get 4 square, and for k2 we get 4 in the denominator. So the powers are 1 less than the number. So we get kn plus 1 of x comma t is equal to xt square divided by 4 to the power n. Now we will find the resolvent kernel r of x comma t comma 1 is equal to summation n is equal to 0 to infinity. What is our lambda? Lambda is 1. So we'll be left only with kn plus 1 of x comma t, and that is equal to summation n is equal to 0 to infinity xt squared divided by 4 to the power n. So that is equal to xt squared can be taken outside. Summation n is equal to 0 to infinity 1 by 4 the whole power n. This is a geometric series, and the series sum will be equal to xt squared. This is numerator 1 divided by 1 minus 1 by 4. If your r for the geometric series summation r power n, since summation r power n is equal to 1 divided by 1 minus r, n is equal to 0 to infinity, we get 1 divided by 1 minus 4. Your r should be, modulus of r should be strictly less than 1. So here we get xt squared 4 divided by 3. This is our resolvent kernel. So y of x will be equal to f of x plus lambda is 1 here, 0 to 1. Whatever is here, this is the resolvent kernel, xt squared 4 by 3 into f of t into dt. We have to replace the variables, right? We have to replace the variables. Y of x is actually phi of x, and f of x is as it is f of x, plus the constant terms are x 4 by 3 integral 0 to 1 t squared into f of t dt. And this t squared is actually y. So f of x plus 4x by 3 integral 0 to 1 this is y squared f of y into dy. So when you see here the options, the option 4 holds. Here they have taken in terms of x, and here we have y. This doesn't matter because the limit is actually 0 to 1. It is for the finite limit, it is for y. So similarly we can have with this new variable x itself. That is not a problem. Both are same. So option D holds. Next question from part C. The integral equation integral a to x k of x comma y into phi of y into dy is equal to f of x. This is a Volterra integral equation of first kind. So here we have integral a to x k of x comma y into phi of y dy is equal to f of x. Now they have given kernel is not equal to 0 for all x can be transformed to, they are transforming the equation to phi of x plus integral a to x g of x comma y into phi of y dy is equal to g of x. So by using Leibnitz rule, I'm going to differentiate this one. When we differentiate, the left part is dy dx outside and this will be f dash of x, right? So when you differentiate this integral, you will find integral a to x dou by dou x of kernel k of x comma y into phi of y dy, and then the upper limit will be x, right? So here plus d by dx of your upper limit into k of x comma x. Wherever y comes, you have to put x, k of x comma x, and into y of phi of x, and then the lower limit is a is a constant. When you differentiate a constant, it will become 0. So the lower limit will be 0. So the lower part, this part would be 0. So we get this type, and this is equal to integral a to x dou by dou x of k of x comma y into phi of y dy, and d by dx of x will be 1. So we get k of x comma x into phi of x is equal to f dash of x. When you compare these two equations, this, let me take it as first equation and second equation, g of x is equal to f dash of x. So g of x is equal to f dash of x. See, look at the option g is equal to f dash. This one holds. G is equal to f. So this one fails. And g is equal to, we have to, let us find small g, not capital G. Small g is equal to, here they have given something. So we will just verify. G is equal to f they have given. So this option is also false. We have to verify these two options. And then here phi of x into k of x comma x, and it is phi of x. Both are equal. For equation 1 and equation 2 are equal. So when you equate the right hand side, we get g of x is equal to f dash of x. When you equate the left hand side, we get k of the function which is having phi of x has coefficient 1 here, and here k of x comma x. So k of x comma x should be equal to 1. And then you find k of x comma x is equal to 1 here. Yes, it is true. And this also getting true, g is equal to f dash. We have to verify for capital G. And similarly here we have to find for capital G. Capital G is equal to g of x comma y is actually equal to the integral part, which is dou by dou x of k of x comma y. When you see the first option, it is exactly the same thing. So the first option is true. And when you see here, k of x comma x is actually equal to 1, right? So when you have g is equal to 1 into dou k by dou x, so we get the same thing. So this also holds. This is true. And g of x is equal to f dash of x divided by k of x comma x. K of x comma x is actually equal to 1. So we get f dash of x divided by 1 is again f dash of x. So we get this option is also true. So first and the third options are the correct options. Thank you.